I welcome all of you to our class. In today's class, we'll continue with the deflection of the beams. Before we go ahead in understanding the deflection of the beams, let's recall what we have done till now. We'll also try to brush up few concepts that we have done previously. In the last class, we were talking about the deformation of the beams, and the deformation we were talking about in terms of the stresses or the strains reduced at a given section of the beam or at a given plane of the beam whose distance from the neutral axis was specified. I mean to say, we had isolated a section of the beam, and this section of the beam that we had isolated, we had located the element distance as delta x is equal to delta s at a distance y from the longitudinal axis of the beam, or what we also call as the neutral axis of the beam. Okay, then as the beam was subjected to deformation, the upper portion of this beam, the upper surface of this beam underwent the compression, and the lower surface of this beam underwent the tension. That is, in the upper surface of the beam there is compression, in the lower surface of the beam there is extension. Fine. And the distance that we had, and the element, or sorry, the length of delta s that we had taken at a distance y from the neutral axis, its length is also changing. Now its length becomes delta s prime. Okay, the upper surface of the beam undergoes compression, the lower surface of the beam undergoes extension. There is a surface in between the upper surface and the lower surface which neither undergoes extension nor undergoes compression, and we call that as the neutral plane. Fine. And when we see the neutral plane from the side view, it looks in the form of, it turns out to be an axis, what we also call as a neutral axis. Okay, now how much strain this element at a distance y, or this line at a distance y from the neutral axis undergoes, we had calculated it yesterday in the previous class, and it was coming out equal, the strain produced in it was equal minus y by rho. That is, the section, the strain produced in the line element at a distance y from the neutral axis was coming out equal, strain is equal minus y by rho. As far as rho is concerned, rho is the radius of curvature. Okay, and it's constant. Now this strain is the strain which varies with the distance y from the neutral axis. What does that mean? In order to make you understand, what I will do, I will go back to this diagram, and in this diagram we say, we have just derived strain is equal minus y divided by rho. At the neutral axis, the value of y is equal to 0. Okay, so when the value of y is equal to 0, therefore the value of strain at neutral axis is equal to 0. The value of strain at neutral axis is equal to 0. That's what we were saying, that at neutral axis there is neither tension nor compression. The element at the neutral axis behaves at it as it's not strained at all. Okay, now if you look y, if the distance is, if this is a say for example this is the rectangular cross section beam, then let's suppose this is the distance c. Okay, then this strain will be maximum. Okay, the strain will be maximum when the value of this y is maximum. Fine. Now the value of the y is maximum at two ends of this beam from the neutral axis. That is like this. This is the section of the beam that we have isolated. Okay, this is a rectangular cross section beam. Essentially the neutral axis will be its centroidal axis. Okay, from here to here the distance will be c, from here to here the distance will also be c. This will be positive and this will be negative. Okay, now what will happen, y is maximum here first. Okay, and we are measuring y in this direction, therefore y is positive, c is positive, therefore strain becomes equal maximum strain at the top surface. Maximum strain at the top surface becomes equal minus c by rho. Okay, since this is negative, it means it's compressive as it's indicated from the diagram as well. If you look at the bottom surface where again our C is maximum, then the value of the strain will become equal. First you have your negative minus, then we have C. We have to take C in the downward direction, that is minus C, and we have our rho. That becomes equal C by rho. Since now the strain is positive, it means the strain is tensile in the lower surface. That's what we had already stated. Okay. So the basic formula that gives us that the variation of the strain across the beam section is strain is equal minus y by rho. This is the basic formula. Okay. Now, this is what we had derived yesterday. And if we, so let me write here, strain is equal minus y by rho, and the maximum strain is equal minus C by rho. Okay, so from here I can write as, if I divide strain by maximum strain. Okay, and if we take, since maximum strain is at the top surface of the beam, it's at the top, it's at the bottom surface of the beam. At the top it's compressive, and at the bottom it is tensile. Okay, let me take the bottom into consideration. That is, if we take the positive of this, you are free enough to do it, then E by E max becomes equal minus y by rho divided by C by rho, that is rho by C. That becomes equal minus y by C, that is this formula. Okay, this formula gives us the variation, the relationship between the strain and the maximum strain in the beam. Okay, so this is quite indicative, and we had already talked about it in the previous class. Now what is very important for us is the understanding of the Fluctuation formula. What does the Fluctuation formula mean? As far as the Fluctuation formula is concerned, look at this section of the beam. This is quite interesting picture in front of us. This picture demonstrates many things, and I think this is a very important picture that's given to us. We had a specimen of wood. Before I go to the Fluctuation formula, let me state what we are trying to do. We have a section, we have a beam. Okay, we had a piece of wood, or what we say, the wood specimen, and this wood specimen was subjected to loads. As it was loaded, this wood section underwent the deformation like this. This wood section underwent the deformation. Okay, finally, as we kept on increasing the load, the breakage happened, and this type of section was seen. Okay, so if you look at this broken section, what has happened, the fibers of the wood have been disengaged from each other. They have been disassociated from each other. It means that this section was, there's something, what we call as, there is an additional section on there must be one more portion of this piece on this side, because under this deformation, under this failure, this piece of wood is broken into two pieces. Okay, so if you look at this section, what has happened at these very sections, it's like the things have been pulled apart. Okay, it's like they have been pulled. So when we say they have been pulled, it is an indication that it was subjected to a force in this direction. It was subjected to forces in this direction. And if you take any small section out here, you can simply say this was the normal stress was created on each section of this very piece of wood. Okay, first of all, physical inspection of this specimen is very important, because the way the specimen has failed, it's quite indicative that the fibers have as if been pulled apart. Okay, they have been pulled apart, and pulled apart means each fiber has been subjected to some normal force. Normal force subjection means a normal stress. Okay, now how much is the normal stress created? That's very important for us. Okay, so we just saw that the value of the strain, the value of the strain is equal minus y by c, the maximum strain. Okay, if this material is loaded in such a way that there is a linear equation between stress and strain, by saying there is a linear equation between stress and strain, I mean to say that stress produced in the section is equal to Young's modulus times the strain. Okay, then if we multiply both sides of this with the Young's modulus of elasticity, then Young's modulus of elasticity multiplied by the strain means the stress. Therefore, we can write sigma is equal Young's modulus multiplied by the maximum strain gives the maximum stress. Therefore, it will be stress is equal to minus y by c into sigma max. Okay, sigma is equal to minus y by c sigma max. That's what is given here in the Fluctuation formula. Sigma is equal to minus y by c sigma max. Now from this formula, we can at least say that sigma is a linear function of y. When y is equal to 0, that is here, the value of the stress sigma will be equal to 0. Normal stress in it is equal to 0. Okay. And when y is equal to plus c, that is when you are here you have plus c. Okay, then c and c will go, sigma will become equal minus sigma x. It will be negative of sigma x. That's why it has been drawn in this direction. When you are here at the bottom surface, okay, if this axis is a symmetric axis, which we will prove later on, it will be the centroidal axis, and sigma will become equal positive sigma x. That is, here the stress will be the maximum and it will be positive. Okay, so it will be along the positive x-axis here, and here it's negative, it will be the negative x-axis. Okay, so this formula sigma is equal to minus y by c into sigma max. This formula gives us the variation of the normal stress in the beam as we move a distance y from the neutral axis. Okay, so we were saying that as the beam is loaded, you will be having a section out here, because what has been done is here we have taken a small section. Okay, we have taken a section out of this beam, and then we are doing the force balance. But essentially, actually, this portion of the beam will be in contact with this portion of the beam, right? And these forces are created on this beam in response to the external deforming force by this section of the beam. These forces are on this section only because this section is there. If this section is not there, then these forces will not be there. Okay, so the thing is that the forces are created. So this sigma max and multiplied by the small area delta A gives us the small force that is acting on a small cross section. The question is how. It will be like, let's go to this diagram here. Okay, so this is what I just want to make you understand, that as the beam is loaded, okay, and you are taking this section into consideration, on this section we just saw that there is a stress variation such that stress is equal to minus y by c into sigma max. Stress is equal to minus y by c into sigma max. So when there is stress, we essentially define stress as force per unit area. This is the normal stress. And we write force is equal to stress multiplied by area. Okay. So it means on each area, there must be some force. That's what has been given here in the form of dF. That is, if you take a small element here, small area element whose area is dA, then if you multiply, let's suppose at this area element, which is a very, very small element, the stress value is sigma. Then sigma multiplied by dA will be equal dF. Sigma multiplied by dA will be equal to dF. That is, stress multiplied by area gives us the small force that is present on this very area that's present on this area. Okay. Now, something very important for us, that when we have a beam, and if we treat this to be our x-axis, this we treat our y-axis, and say for example this beam is loaded by some force, this force that we apply, external deforming force, that will be along the y-axis. Beam is not loaded along x-axis. That is, summation of all the forces acting on the beam along x-axis is always equal to 0. It's always equal to 0. Now, how much will be the force? The force is dF on a small area element dA. How much will be the total force acting on this area? Okay, this dF is a small force acting on the area, small area element dA. Total area for us is A. How much will be the total force? That will be integral dF. That is equal to integral dF is equal to sigma dA. Okay, sigma dA is equal 0. Okay, and we have just seen that we can write this integral sigma, we can write as minus y by c sigma max, and we have our dA is equal to 0. Therefore, we can write sigma max divided by c integral y dA is equal to 0. Sigma max cannot be 0. C cannot be 0. Therefore, this integral y dA is equal to 0. What does integral y dA equal to 0 mean? That is something very important. That is, we are getting integral y dA equal to 0. What does that mean? That is, if we have an area A, okay, let's suppose this is the centroid of this area. Then the x and y coordinates of the centroid are given as x bar is equal to integral x dA divided by integral dA. And the y coordinate of the centroid is given as y bar is equal to y dA divided by integral dA. Now, when we have integral y dA equal to 0, when integral y dA equal to 0, that means y bar is equal to 0. What does that mean? Y bar is equal to 0 means the y coordinate of the centroid is 0. Y coordinate of the centroid is 0 means the centroid lies at the origin of our xy system. This is the x bar. When y bar is equal to 0, it indicates that the centroid lies at the center of our xy system. Okay, and the x-axis and the y-axis are what we call as the centroidal axis. This is the centroidal axis. This is the centroidal axis. And if we look here, we had just treated this x-axis to be our centroidal axis, but right now we are saying that this axis is our neutral axis. So for us, in this case, the neutral axis is equal to the centroidal axis. The neutral axis of a beam is equal to the centroidal axis. This is what we are getting when we do the force balance along the x-axis. Number one. Number two is, if we do the moment balance, that is something very tricky. Moment balance is, this force will also along this force, small force dF is acting in this direction, this direction, this direction. Okay, fine. Now this force is having, each force component, each force vector is having some y distance from the neutral axis plane, from the neutral plane. Okay, let me take this dF. How much is the moment of this dF about the z-axis? Because this is the force arm. Let me clear it. dF is acting in this direction. This is dF. This is the y component. Sorry, this is the distance from the neutral plane. Okay, therefore moment of this force will be equal to y dF. This is the moment of this force. Now we have the total force, therefore the total moment will be integral y dF, that is the total moment, and this moment will be along this axis. If you take the right hand screw rule, okay, this is what is the moment along the z axis. Okay, this we can further write as integral y dF can be written as sigma dA. Okay, and we can further write this as integral y. In place of sigma, we'll write y by c sigma max into dA. What we have actually, sigma is equal to minus y by c into sigma. But if you look at this moment, this tries to rotate this element in the clockwise direction. Therefore, we take this moment as minus, and minus minus will be plus. Okay, so this will be equal sigma max divided by c integral y square dA is equal to the moment along z-axis. Okay, we can further write this equation as, and we know as far as this y square dA is concerned, this y square dA is known as the second moment of area. Okay, and we write this as I. So m becomes equal sigma max divided by c into I, where I is equal integral of y square dA. This is called the second moment of area. Okay, now as we go ahead, what we have is this equation, sigma max. We go to the next page. Sigma max is equal m into c divided by I. This is the maximum value, and this maximum value of the stress is at a distance c from the neutral axis. If we are at a distance y from the neutral axis, then sigma will be equal to m. In place of c, we'll write y divided by I. Sigma is equal to my divided by I, and this is what we call as the Fluctuation formula. Fine. Now it is this formula that we make use of in dealing with the deflection of the deflection of the beams. Okay, as we had here in the yesterday's class, we were talking about these equations. Okay, in the yesterday's class, we made use of this sigma is equal to minus my by I. In yesterday's class, we were talking about this Fluctuation formula. Okay, now what we have in hand is 1 by rho. Let me recall the yesterday's lecture. We had this formula in hand yesterday, that is 1 by rho is equal m by ei. Okay, now bending moment in the beam can be calculated. E is given, I we can calculate. Now TDS is this rho, okay, the curvature of the beam. Now what we do, we make use of the calculus in calculating this curvature. How we do it? That's very easy. That is, as far as the beam is concerned, now we had a beam like this, okay, and under the influence of the external load, the beam deforms like this, say for example. Okay, so if we treat this to be our x-axis, and we say these are the deflections which are represented by nu. Okay, then if you look at this curve will be having some radius. Okay, that is what we represent by rho. Then we know from the calculus, the formula of the curvature is given as 1 by rho is equal d2 nu by dx2 whole divided by 1 plus d nu by dx square whole raised to power 3 by 2. This is what we do from the calculus or the mathematics. We need not to derive this curvature formula. Right? Now, as far as this d nu by dx is concerned, this d nu by dx has to be very, very small. This d nu by dx has to be very, very small. In fact, approximately it can be taken as 0, or it can be, its value is very, very small when it's compared to 1. There is a reason for it. The deflection in the beam should be very small. The deflection curve should not be abrupt. The value of the deflection should not be large. When the value of the deflection is large, then the value of this d nu by dx will also be large. When the value of this d nu by dx is very, very small, when the value of this deflection nu is very small, the value of this d nu by dx will approximately be equal to 0, because this tangent at any point will almost be parallel to x-axis. Okay, so we can neglect this d nu by dx in the case of the beams, because we want the beams to be having the least slope. Okay, slope of the curves should be small, because if you have the large curves, then it means the beam has sank, the failure chances are more. So we can, and so neglect this, we can write 1 by rho is equal d2 nu by dx2. But we just had 1 by rho is equal m by ei. Therefore, we can write the bending moment in the beam m of x is equal ei d2 nu by dx2. And this equation is the equation that will be used in calculating the deflection in the beams. Okay, because we have to find this equation, we have to find how nu varies, how nu is a function of x, and the nu as a function of x can only be obtained once we solve this equation. Okay, once we solve this equation, from this equation we already know that we can calculate the value of m, that will be known to us, e is known to us, I is known to us. Then using the integration methods, we can calculate the value of this deflection nu. That's one thing. One important thing from here is some important formulas that we should be having in mind while we are solving the once we are taking the beam deflection into consideration. That is, we write d we write ei d2 nu by dx2 is equal to m. But we know from the previous class that shear force in the beam is equal dm by dx. That is, if we differentiate this equation, that is d by dx ei d2 nu by dx2 is equal dm by dx, that's equal v. That is ei, when ei is constant, d2 nu d cube nu d3 nu, okay, dx3, because we have dx will be equal to v. This is one more equation of the beams. Okay, we also know that uh, the load, intensity of the load on the beam is given as dv by dx. Now if we differentiate this equation, we'll get ei d4 nu by dx4 is equal w, that is the intensity of the load. So these are the different formulas that we will be using in solving the beam equations, and these formulas are also given over here. These formulas are given over here, and it is these formulas with the help of which we'll be solving the beam equations, we'll be solving the beam problems. Now let's go to the problem section.